Welcome to CIGRE 2024. In the Paris session, Working Group B277 will present a tutorial based on the risk modeling for overhead line networks. And this video is prepared in lieu of identifying all the input and the parameters associated with the actual model. So let's get straight into it. The model that I will demonstrate as an input is provided as an Excel file. So the first item on the Excel file is related to the change log. As you can see, the team has put a lot of effort in terms of preparing this model. There's a version register, and as of today, we are at 1.8 G, which G stands for Google Sheets. So the Excel file is transferred into Google Sheets, and we will provide the access to the working group members for their comments and their input. So the synopsis of this working group target was associated with the actual risk management of overhead line networks, preparing a model for identifying, evaluating, and basically identifying the mitigation of the operational risks. Now, as a result, we will have there's some texts here that you will see, and there's a related text associated with the actual model. And so, the first sheet that we have to focus on is called the original network case. So, as a user, as an input person who understands the network, the current network that you are evaluating the risk for, you have to look at the first sheet as your starting base. Now, this first sheet is called original network case. The way the first sheet operates, you will have a network importance characteristic or set of characteristics that are associated with network importance. Now, these characteristics are, for example, circuit electrical utilization, connected generation, whether it's an interconnector or not, what's the directly connected demand, value of the lost load, physical network situation, whether there are any neighboring assets, neighboring lines. Then you have a characteristic of overhead line configuration, whether it's a single circuit or double circuit or anything special associated with the configuration. Then you've got a field or a characteristic associated with regulatory scrutiny level. Now, these characteristics, is important to note that the working group team has established these characteristics, but there may be others that perhaps the working group has not captured. Now, risk modeling is a very vast area whereby there will be numerous elements that will come and go as the user will see fit. However, this model gives you at least the baseline of all the important characteristics that are associated with network importance. So, how to populate the relevant fields into this tool or this model? For network importance, you have, for example, let's pick up one. Let's say directly connected demand. So, if you know that your current network is, say, for example, have a directly connected demand of greater than 500 megawatts, you just simply pick up 500 megawatts. If you have, say, if you know that your generation is less than 30 megawatts, you can pick that up as well. Now, for distribution, you obviously have a lower load associated with the demand that I've just demonstrated there. That's not an issue. You can obviously put 30 megawatts as your lowest limiting number, and then you can increase or decrease the weighting. The two cells that you have the ability to input are the cells D, the columns D and columns E, whereby you can pick up the criteria and then you can also play with the weighting. The weighting will give you the ability to enhance or decrease the weighting of a certain characteristics. For example, if you know that your distribution line or transmission line has a certain directly connected demand that perhaps from your perspective has got a higher emphasis, you can increase the weighting. But overall, the weighting has to summate to 100. That's how the model works. And we've obviously normalized, as you can see on the right hand side, we've normalized the scoring to effectively reach a common set number. Now, all these scores that you are seeing on the column E are effectively associated with a set of data that we've inputted into a sheet called data at the bottom here. I'll just quickly go through that and just demonstrate how that is linked to this input field. In data, For example, if we're talking about the network importance that we were talking about earlier, and all the associated characteristics associated with circuit utilization, or in our case, we're talking about the directly connected demand. We have 500 megawatts, 250 megawatts, and you see the scoring associated with the higher the megawatts that are connected to our circuit or our network, the higher the rating, the higher the score that we've purposely given. Now, if you were to suggest a different rating or a different scoring associated with these individual characteristics, you can do that. That we've kept that field open. You can play with this number. You can make it 9. You can make it 7. But primarily, we recommend to keep it between 1 to 10 so that you can have a common set of normalized output that we have linked the model to. So once that's done, as you can see, there will be a numerous. This is the data set of the entire model, and if you start from the top all the way down, you will see that all of the individual cells that are linked to this data set are then used in the model. So if I scroll down to give you a view, you have things like restoration complexity, which is one of the characteristics that we talk about, where you have all these individual items around accessibility, spares, and then you've got the numbering. And there's a reason behind the scoring that we've ascertained or that we've inputted here. For example, you've got if the line components are based on a standard code, less than 20 years old, so you will have a lower risk. But if they're no longer available, then obviously there's a higher risk. So therefore, you'd have a higher number. So that's the logic behind picking up the relevant, the relevant characteristic and the relevant scoring for that item. Another example, perhaps, is if you're restoring a certain line and you've got all of your resources lined up in case of an extreme weather event where the certain line goes down, you need to basically pick up all your resources and mobilize to site. Now if you can do that within 12 hours, you have a lower risk, therefore you have the scoring of 1. However, if you don't have any resources up to 72 hours or so, which means there's going to be an extended outage, which means there's going to be extensive loss, and to the whole economics, the whole chain of events, you'll have losses, customers all out, then obviously that's a higher risk. Therefore, you have a higher number of 10. Now, that's the thinking behind the actual values in this data sheet. And you can keep going down and you can see all of these elements associated with the planned maintenance, unplanned maintenance. For distribution specifically, we've got the SAIDI and the SAFE numbers here associated with the actual availability of the distribution networks, which you can link also to transmission networks, and therefore the risk rating associated with those numbers are high and low depending on which level of outage or loss you're looking at. Now, last one, and we'll jump out of this sheet. Last one is, let's take a simple example of high winds. Now, if we know that there's going to be a Category 5 hurricane going through, a certain network, and if you have seen that from your root vulnerability analysis, from your desktop assessment, or whatever geographical assessment you've done, you will quickly see that if it's a Category 5 hurricane with a 157 miles per hour wind speed, you will have a higher risk number, which is 10. But if you know that this line is less than 33 meters per second, and we know that in the route, this route is not vulnerable to extreme weather events of wind, therefore you have a lower number. So I think I've explained that quite in a lot of detail. So I'll jump off this spreadsheet, data sheet, and go back to the original network case. Now, that is the thinking behind each item. And now you will pick up these items and you will basically input your network characteristics line by line. For example, is your line double circuit, single circuit? You just literally go and say double circuit. Or if it's a single circuit, you'll just say single circuit. In this case, let's just leave it as single circuit. Then you will go to route accessibility. If you know that your route basically has route access has been stopped by major events, then you pick up that. That's the higher risk number. But if you know that you have at least 2 major highways within the route that can access your network or your assets, then you pick up that, and then you will see a lower number. However, you can always remember, play with the weighting. You can increase the weighting or decrease the weighting, because that is your ability to put a certain focus on a certain item associated with your task. So the other bits of information, so that was around network importance. Then you got restoration complexity. Remember, these 4 parameters in the synopsis are how we have built the model. So if I go back to the synopsis, network importance being 1, restoration complexity being 2, historical performance being 3, and root vulnerability being 4. These are the 4 essential elements of our model that give the user, the network operator, the regulator, whosoever is using the spreadsheet, to get a view of the risk rating of a certain overhead line network. These are the 4 principal parameters or characteristics that we are analyzing in our model. So that's very important to understand. Now, going back, all of the inputs associated with network importance, restoration complexity, and then you've got the historical performance, where you know as a network operator, perhaps you don't know, but then you can get the information from the right resource or the right source. For example, is your conductor or earth wire or any cable in the network that you're looking at in a poor condition, current state? Remember, this is the current original network condition from our records. So you will just say C6, very poor, urgent attention. The C's are all just a code given to remember perhaps that C6 is poor and C1 is pretty good. However, the actual scoring, if I were to pick C1, excellent condition, then the risk would be 1, which is lower risk. But if I pick up very poor, then it's 10, which is a higher number. So after that, you will see that we have got historical performance, and historical performance number 2, which is around the SAFE, SAIDI, and the faults per year. Then you have planned maintenance. You've got extreme wind or induced ice events, ground induced failures, erosions, earthquakes, lightning strikes. Now this is all based on your available data that you got from your network modelers or from your network operators or asset owners or asset managers. They can provide you with that data, which will flow into your network analysis. And then you would say, okay, I know, for example, there's been a flooding event in my this specific line, which is 6 to 10 extreme events in the last 5 years. I have data. I can actually put this in there, and then you will have a certain risk rating. In this case, I've just put the extreme, which is 35 extreme events in a given 5-year period. So that gives you the most higher number. Now, going forward, you will have things like the age of the asset, the spec that it was designed for, the performance on the steel, the conductors, whether they're overutilized or underutilized. So you can input all of that together. Once that's done, so you've basically covered the network importance, restoration complexity, historical performance. Then the fourth one, being the most important one, is root vulnerability. This is where you will have to play with in terms of your understanding whether this route has observed or will have been will have seen or will see certain events which will be extreme. Now this is where if it's a distribution line, especially important, fire. So you need to say multiple fire outbreaks along the route, pole fires, for example. So you can click that. If it's not a distribution line, it's a transmission line, that still applies. You'll have multiple fire outbreaks within the region because of vegetation or whatever reason, and then you can put that number in, which gives you the highest risk rating. And then you've got extreme cold. You know that the route that you're analyzing has extreme cold events such as avalanches or such as ice storm or rime ice accumulation. So you would pick that relevant number. High winds and things like that. Now, once this bit is inputted as a root vulnerability, the only thing that is different to the one previously where you had the historical performance, where you were inputting what you know had happened, is the likelihood of occurrence that may actually, from your perspective, may occur again. And that's where you need to enter the likelihood occurrence of each individual network risk that you think may actually happen as an extreme weather event. So, for example, you know that there's, say, for example, we pick up the social impact. We know that there's been a major vandalism in a certain segment of this corridor that we're analyzing. So we will put major vandalism as an input, and the likelihood of occurrence of major vandalism being unlikely is another element that you have to add, and that will give you a rating of 2. If you were to say that vandalism is quite prevalent in that region, then you obviously have to put in likely to occur, which will increase the risk rating to 5. So a combination of the root vulnerability analysis with the likelihood of occurrence will give you an indication of how vulnerable is your route. Once that input is complete, Then you have to go into what is called the sheet called network changes that are needed. Now, in this, the difference between the original network case and the network changes needed is your wish list. So, for example, I know for a fact that if I were to invest my energy and time as an asset owner and operator on the condition assessment of my network, whereby I'm going to replace conductor, and I know I've done that in the last year, then obviously my original network case, I had the conductor condition as very poor. But in the new network change case, I will make that as excellent to good condition because I've actually made that happen. So the relevant fields associated with anything different to the original network case is your opportunity to input into this line. For example, if my original connected generation was 1 gigawatts, but I know now that going forward I will have this segment of the network that I'm analyzing will turn into an interconnector. So therefore, the risk rating will change. What it was is no longer applicable, and what it will be is going to be an interconnector. So you have to input the interconnector as greater than 2 gigawatts, or is this a major interconnector, for example? And the answer is yes, we will put that. So see that score 10, which was previously for the same cell 8, is now different, right? So you've obviously increased. In this case, the risk of that specific segment has increased, not decreased. So your route rating or your rating of the specific segment of the network that you're looking at has increased. Therefore, you have to capture what is going to change. And that's why the spreadsheet is called network change. So another example will be if you know that you have your age of assets, you've replaced certain assets in your network, and no longer in the previous case you had these as, for example, most of the assets or most of the components in the network were greater than 75% of age, which was quite a higher risk associated with the age itself. Now, in this case, you will do an input which will be saying, for example, 21 to 35%. So this spreadsheet gives you a snapshot of what's changed or what may change with an associated targeted response, and hence the route rating will change. Once that's done, then you effectively populated two snapshots of your network. One is existing, historical, and one is what's changed, where you've actually put a targeted response to and associated asset management plan to. However, there's one more element that we have to talk about: vulnerability. Now, the third spreadsheet, vulnerability, is where you know that you can actually create a mitigation which will effectively be either a preventative mitigation, which would be preventative measure, or you will carry out a mitigation that is associated with something inherent with the design, or you will remove the risk. Therefore, you will have a residual risk. Now, in this spreadsheet, you will have the ability to look at those extreme root vulnerability, extreme event analysis, and you actually can play with this by looking at which area is the most sensitive and which area creates the most impact. For example, if you were to look at the vegetation in your existing network of 25% on the route, but now you know that you can actually have there's no vegetation risk. So you can just say no vegetation risk, and that will give you a differential factor of 86%. Or, for example, if you were to say 50%, so this will give you the weighting. Now, in this case, that 86 is coming from the weighted mitigations, and I'll show you that in a second. So let's take another example. If you know, for example, that you have a tsunami risk in your original input, but in the new associated development work that you've done, you can say that, look, I have actually mitigated this risk by eliminating the tsunami impact on my network, by creating some rerouting or anything, and there's no extreme water risk. So that gives you that ability as well. Now, for example, multiple fire outbreaks you had previously, and now you're saying there are no fires in this network because I've actually eliminated that risk. So you can say that, and therefore these numbers will give you an average net risk reduction because you've mitigated and you've actually placed a mitigation on these elements associated with the changes between what was and what is. So where do we get these net risk reduction numbers? I'll go through that now. That is coming from mitigations weighted. Now, this is a very detailed spreadsheet in which you will see that there's a number of elements associated with the regulatory compliance, network stability, health and safety, and this is coming from the earlier recommendation of the technical brochure 598, which we've utilized and enhanced. And in each one of these items, we are carrying out a weighting analysis, therefore giving us a number associated with the probability of occurrence, such as, let's say, take fire, for example. Now, the value of the loss load, we know it's severe if there's a fire event and it knocks out a distribution line or a transmission line. So you put severe, right? Or you put major, and that will give you a weighting. And all of these relevant boxes are associated with that weighting characteristic. I'll leave the severe here. And this will give you a number, an impact risk associated with that extreme weather event or extreme event. And then what are the preventative measures as per the technical brochure 598? There's a what can you do to eliminate that risk of bushfires? You can add rapid earthfall current limiters, perhaps. You can add rerouting on your bushfire zones. All of this will give you a residual risk, and that extreme risk will go down to moderate risk. And therefore, that magic number of 51%, I think it was previously, comes from that differential analysis. Now, you can play with these individual boxes of whether you think a bushfire risk is extreme or moderate, and you can get a different weighting, and therefore that will come back to your original spreadsheet of vulnerability changes, and therefore that percentage will be associated with what you think is practical. But in this case, we've said it's 51% for a bushfire mitigation strategy and a preventative measure. I hope that's clear. And then once all of these 1, 2, and 3 individual sheets are populated, then you're pretty much straight into the results summary. Now, in this case, we had an existing network condition rating of 3.66, which is basically provided in that formula. Once we carried out the network changes associated with what we thought we can actually deploy, we have a reduced network status of 1.24, which means that you've actually carried out certain targeted tasks. Therefore, it's measurable, it's specific. What have you actually done to reduce the 3.66 down to 1.24 as a differential number? Now, if you were to deploy the specific mitigation from the weighted measures, the preventative measures that I talked about earlier in the vulnerability changes, that gives you an additional boost, which means more money, more effort, and therefore the root rating index will further decrease down to 0.9. So the science behind the risk rating or the root rating index is what you have will give you a number. What you will have changed in your network where you've deployed new assets or new agent, you've improved the design, you've improved the routing, you've improved the, and sometimes that may actually go other way. If you know that your network has suddenly become an interconnector, it may actually increase. So this differential overall is what you're looking for as a risk manager. But effectively, the residual risk also should decrease if you've done the right steps associated with the preventative measures. So all in all, this spreadsheet provides this view that you're seeing on your sheet, which is called results summary. I would like you to have a play with it, put as many case studies in it, and then we can have a discussion in the comment section, or you can contact me to talk about any specific examples that you may have. But I believe that we have enough data set that is available, and you will have the ability to play with this in a great detail. Thank you very much for giving us the time, giving me the ability to present this to you, and I hope to hear from you very soon.